And welcome back everyone to the History of Mathematics. We're continuing our work through Stuart Hollingattle's book Makers of Mathematics, and we're talking about chapter 12 on the mathematics of Leonhard Euler. In this video we're going to discuss Euler's contribution to a branch of mathematics called graph theory. Now, in the context of this video, when we talk about a graph, we're talking about something a little bit different than what we deal with in calculus and algebra. We're talking about basically like a network. So a graph, in this sense, allows us to deal with kind of connections between basically anything. It can be very abstract. Okay, so the kind of genius of Euler's work in this is in the simplicity with which he is able to see the problem, viewing just what is essential in the situation rather than some extraneous details and so forth and so on. So the whole business starts with the so-called Konigsberg bridges problem. So let's go ahead and take a look at that. Let's switch over to the document. So here we are looking at a simplified version of the city of Konigsberg. So we have kind of a river running through the city, we have a couple of islands, and we have a bunch of bridges. Looks like we got 7 bridges connecting the shores to the islands. So the question that people were asking in the city of Konigsberg was, okay, let's say I live over here on shore B. Can I take a walk that traverses each of the bridges exactly once and end up back where I started? So in other words, I want to go out for a little recreation and I want to make a tour that goes over every bridge exactly once and lets me get back home. Okay, so the way Euler solved this problem was to kind of make it a little abstract. Okay, we don't need to talk about islands and bridges, we can just talk about connections between these land masses. Okay, so when we're talking about graph theory, we're talking about vertices and edges. A vertex, in this case, will be represented by a dot, and an edge will be represented by a line. Okay, so in this graph, I've got 1, 2, 3, 4, 5 vertices, and 1, 2, 3, 4, 5, 6, 7, 8 edges. There's no vertex right there. The 2 edges cross, but I could do an equivalent graph that doesn't have them crossing. Okay, remember, when we're talking about graph theory, we're talking about connections, not necessarily how they're connected, but that they are connected. So instead of cutting right through here, I could just say, okay, there's your connection. So those are equivalent graphs. Okay? All right. So back to the Konigsberg bridges problem. So what Euler did was he represented that situation in the city of Konigsberg by taking every landmass and making it a vertex. Okay, so whether it's a shore or an island, we're going to represent it as a dot in our picture. And the bridges are going to get represented by the vertices. Okay, so what we're going to do is we're going to take this situation involving the land masses and the bridges and translate it into vertices and edges. So here we've got our vertices and edges. So this vertex represents the north shore, These two represent the islands, and this is the south shore. You'll remember the two islands were connected via one bridge, and there were three bridges connecting the north shore to the various islands. Same thing with the south shore. So what Euler says is, all right, we want to basically trace over every edge exactly once and get back to the start point. And right away he sees a problem. And in this particular example, it doesn't matter where you start, you're always going to have the same problem. So let's say you lived on this island. Okay, if you want to traverse all three bridges, what you need to do is you need to leave, then you need to come back, and then you need to leave again. If we just focus on this one, it doesn't matter what's happening over here. You're eventually going to have to do that. If you start here, you need to go out, and if you're going to traverse each of the bridges exactly once, well, you got to come back on one of these, whichever one you pick, and then you'll have to leave via the other one. And now you've used up all the edges coming to this landmass. Okay, now the problem is this is degree 3. Now the degree of a vertex, you can probably guess from the context, the degree of a vertex is the number of edges coming in. So these vertices here are all of degree 3, and this one over here is degree 5. Okay, now whenever you have an odd degree vertex, you're going to run into this problem. Let's say you lived on the center island. You'd have to come out, come back, go out again, come back again, and then leave again. So if you lived on the center island, you run into the same problem. You wouldn't be able to end your trip on the center island. Okay, so Euler's conclusion was that a graph has an Euler circuit. Okay, now an Euler circuit is a path traversing each of the edges exactly once and ending at the same vertex where you started. Okay, so circuit implies we go around and then come back. Okay, so a graph has an Euler circuit if and only if every vertex has even degree. Okay, so if you have even one vertex that has odd degree, that ruins your Euler circuit, basically for the reason that we talked about. You'd have to come in, go back out, and then leave again. So you wouldn't be able to start and stop in the same place for that vertex. So that would be trouble. So to have an Euler circuit, the key is every vertex has to be even degree. And remember that the degree is equal to the number of edges coming into the vertex. Okay, now I would like to look at a related concept, and that is the concept of an Euler walk. Okay, so if you look at that picture that I drew, when I introduced the idea of graph theory to us above, you might remember this. There's a little trick to this. Sometimes you'll see people asking you to trace over this, drawing each edge exactly once. Okay, and it can be done here. All right, so you'll notice, okay, I go something like this, up, down, up. Okay, So you'll notice I traced over each edge exactly once, but if you checked me out there, my starting point was over here, my ending point was over here, right? So I went kind of up, and I made like a little N, and then I went around the top there, and then down, and then over, tracing out that. So that's not exactly an Euler circuit. I did trace over each of the edges exactly once, but I didn't start and end in the same place. So that's called an Euler walk. And you can have an Euler walk if you have exactly two vertices with odd degree. Okay, so remember, if you have anything with odd degree, that precludes you from having an Euler circuit. If you have exactly two, you can have an Euler walk, and you have to start and end at the vertices of odd degree. So Euler basically invented the study of graph theory with his solution to the Konigsberg bridges problem. So that's another one of the many fields of mathematics that Leonhard Euler contributed to. If you remember from the text, Euler published an average of 800 pages of mathematics every year of his working life. So there's going to be lots of different stuff in there. He worked with number theory, mathematical physics, basically you name it, he did something in that field. Okay, so there is a whole heck of a lot to do there. There are still translations of his papers and books underway to this day, and he died over 200 years ago. So truly prodigious output. I do want to do one more video about Euler's work with polyhedra. We talked about Euler's identity. There's something called Euler's formula, which is a little bit more related to the graph theory stuff than it is to the series stuff. So I'll put a link to that video right over here, and that'll be our last one for Leonhard Euler.